Hi. Section 2 of Chapter 1, or Topic 1, or Book 1, whatever you call it. I'm going to call it chapters, so get used to that. No notes to make on this, so just a real quick run through. Key differences in numbers is that sometimes how you apply the numbers to a situation is important. And so those ones are the things that we call vectors, and it's usually down to direction. So the interesting thing when you're looking at vector numbers, for example, velocity, well, it might change its velocity because the size of it has got bigger, so it might go faster or it might go slower. But also, if it goes the same velocity but changes direction, then again you've actually got a change in velocity. So the size and the direction matters. And we need to start thinking about direction in a lot of detail. We'll do that first, but often we can break it down into just things going in straight lines. Okay, so either speeding up, slowing down, for example. Okay, first things first, and I'll say really clear here, we do a lot on forces, so some people just think about forces, but most numbers actually are vectors. The data that we use could be all kinds of different things. Electric current, for example, is a vector because it flows in a certain direction. So don't just fall into the trap of thinking about forces. There are so many others as well. Scalars, again, if you wanted to play the exam game, really energy or power. If they're mentioning those two, it's just how much you've got. It doesn't matter about direction. It's just the total. So when you're adding up things like energy, you just add it all up. There's no issues, or you take it away. Vectors, when you're adding them up, you need to think about the direction as well. So most of the time we can visualize this, and that's the easiest thing. Mathematically we can play with it as well. So if you have a vector A, well, if you add it onto B, it would be going up and it would be going that way. But if you have A and you want to subtract B, well, you go up A, and then instead of along the arrow of B, you go in the opposite direction. So the only difference between 7 and minus 7 is the direction it's flowing in. Okay, so we are going to do a lot of work on adding vectors, but adding can also mean subtract. It all depends on that. So if you are having a tug-of-war team, you're still going to add the vectors of the two teams, but they might cancel out because actually you're subtracting, or more correctly, you're going to add a negative number. Okay, so direction is signified by that negative symbol if we're just going in opposite directions. If we're not, we need to use some techniques, and the best way by far is using parallelogram of vectors, scale diagrams, drawing them. So if I had 7 and I had 2, then that will be, say, 7 centimetres long, and that would be 2 centimetres long. And then you can literally, with a ruler, measure the answer. So we can do things in different ways, and again, here's a wide range of getting different answers from A plus B. That's a straight A plus B, that's an A plus negative B, that's a B plus negative A, and that's going in the opposite direction to that one. So notice the commutative thing, A minus B is the opposite of B minus A, opposite directions, yeah? And then these two as well, negative numbers added together give you the opposite of positive numbers. So that's going that direction, that one's going that direction. So it looks a little bit complicated, but it doesn't need to be. We're often using triangles, but not always. If you've got triangles, there's some maths which are on the back of this page, but actually you may have lots and lots of forces added together, and the only way to do that easily is literally draw them out to scale. Okay, so that's the best thing. If you are trying to add numbers, and rather than, I suggest this heavily, don't try and draw triangles, particularly if it's not a right angle. You're actually better off if you draw your triangle, and then these will be parallel. So draw a parallel one, same size, and then these two will be parallel, so the ones with 3 stripes are parallel, and they'll end up, and you'll see very easily if it's drawn well, because they will be a parallelogram. Okay, so you can either have A plus B, or you can have B plus A. Now I know you've done it in physics, but again in the PowerPoint go into a little bit more detail. So otherwise, to finish off, nice and simple stuff. Pythagoras, everyone's favourite bit of maths. Use that loads, which will obviously give you size of sides. Okay, we can find out any magnitude of any side of any triangle. Really common that we use. You can use the sine rule with angles and things like that, but best by far is actually just using simple right angle trig. So if we can get things into right angle triangles, the maths is so much easier. Cosine rule, perfectly good as well if you want to find things, but actually we don't need either of those at this level. It's often easier to just go straight in with a right angle triangle. Okay, so we'll leave it there. Brush up on these. You know, always useful stuff anyway, but we're going to use these an awful lot, as you will soon find out in this first couple of modules after this. Quick heads up again, if people are looking at this and go, that's not the way we learnt it. All of this could be A over sine A, so we swap them over, and everything would swap over. So A over sine A equals B over sine B equals C over sine C, with the little letters on the top and the capital letters on the bottom. So the sign of the capital letter still just at the bottom, the denominator rather than the numerator in the equation. As long as they're all the same way up, that works fine. Okay, and I haven't bothered writing the cosine rule in there, which I can vaguely remember back through the mist of time, but the reason I only vaguely remember is I don't use it. We don't need to get there. Okay, but if you want to use it, by all means, it's all about just making it nice and clear how you get your answer.